So a very interesting system that can be very useful to understand better the decay in spectroscopy. So for example, in vibrational spectroscopy, when you have the decay of vibration, we will see the classical equivalent, so the damped oscillator. So we might have some kind of friction, of course it will be a vector in the form of minus alpha and the velocity. So if something doesn't move, there will be no friction, otherwise there will be some kind of friction. Now, if we define our damping coefficient as 2 alpha divided m, so this is what we are actually interested in, our damping coefficient, and we call omega 0 our undamped frequency, so the frequency that there will be without this friction, we can see how our system will go to equilibrium, because of course if there is some kind of friction, after a while the system will arrive at equilibrium and won't move anymore. Now there can be three situations: the underdamped oscillator, the overdamped oscillator, and the critically damped oscillator. Let's start with the underdamped one. So, to be underdamped, lambda must be slower than the undamped oscillation. Now, if we have an underdamped oscillation, it means that the oscillator is quite free to move. It's not, the friction is quite low. So we will have a slightly different frequency that will be simply slightly modified by this friction. And we will, on the other hand, have two possible solutions of the equation, depending on the static conditions. But as you see, my oscillator in any case will keep oscillating with always a smaller and smaller amplitude. In fact, the amplitude will decay exponentially. This solution, that is a linear combination of both the solutions, in fact, is a time exponential that will exponentially reduce our amplitude, and then simply something oscillatory, so a cosine with a phase. So this is what you might expect when you have actually something that does oscillate and slowly decays. And actually it's, as seen, the amplitude of the oscillation will decay exponentially. So this is usually what you imagine to see when you make a vibration, when you vibrate something like a molecule and then wait the vibration to stop, and you see this decay if you make some kind of time-dependent spectroscopy. Now another situation can be the overdamped oscillator, where lambda is bigger than the undamped oscillation. This can be considered as the case in which you have a highly viscous medium in which you try to get your oscillation. So, for example, if you put a pendulum inside thick honey, it will simply very slowly reach equilibrium and stop there. And it won't oscillate at all. And as said, the reaching the equilibrium will be slow. You again have two possible solutions depending on the static conditions, and this is the general solution. So it's a linear combination of both solutions. The formula isn't very user-friendly, but that's what we got. This is the last possible situation, and it's the critically damped oscillator. This is the fastest way to reach equilibrium. In this situation, the pendulum will reach equilibrium in the fastest way possible, and again won't oscillate. So, as in the overdamped one, it will go down and then stop, but it will be incredibly fast. There are two possible solutions again, and their linear combination will show us that we will have an amplitude decrease in time that is again an exponential. So we will again see that also in this case the time decrease is an exponential, but this time without any kind of oscillatory contribution.